Right, what's up, guys? Today we're doing the important part, episode 12, and we're doing just some stationary points question, a bit of a shorter episode today. Just going to be going through some questions on stationary points. It's mainly for AS kind of level questions, but you can do it if you're looking at the GCSE Further Maths curriculum. So we're going to start with this question here. So this is just classic stationary point question. So firstly we're just going to differentiate. We're going to as we do with stationary points, you're going to see that it's quite a theme. And we can see that the gradient is -3 at this point here. So we're going to substitute 2 in as the x and say it equals to -3. Next, we are going to just simplify this down and find a, just to show that it's a. And for b, we're going to know that f of 2 equals 10 because it says that there's a point 210 that lies on that curve, and from that we can find that b is 44 because we have the rest of the equation. Alright, next we're going to just differentiate. We're going to rewrite the differentiated version with the a in, and we're going to show that it has no stationary point, so we're just going to use a discriminant here, and we're going to say that it is less than 0, which means that there are no solutions, which means there are no stationary points because the derivative has no solutions. Right, next they've added some algebraic long division in, but you just divide it whatever way you want to. There's multiple different ways, but this is the quadratic you get from it. And next you just use a graphing calculator for this question. You just substitute 0.2 in for x, 0.2x in for x, and then put them both on a graph and get these points. I mean, it's obvious that the point will be 0 and 44 because the y-intercept stays the same, but the other point has been more difficult to find without using a graphing calculator. Right, next question. I've skipped the second question because I've already mentioned it in a previous video and it was quite easy as well. So we're going to do the 6 marker here. It doesn't give you any parts to really work with to help you with the question, it just throws you in, but it's fine because it's not that bad. It tells you the derivative first, so we're going to substitute 4 in because we know that it's the stationary point, and so we know the f dash of x equals 0, and we're going to get this equation here, and you can probably tell by now that we're going to have to solve simultaneous equations at some point. Next we're going to integrate it to get the main function with a and b. It tells us that the y-intercept is -5, so we don't have to bother finding c. And then we're going to substitute 4 in because we know that f of 4 equals 3 because it's a point, the stationary point is just like any point where it should give you this output here. And then we're going to simplify and simplify and simplify more and simplify more. Then we're going to bring back the equation from earlier, 2a plus b equals -16, and we're going to solve these simultaneous equations here. Now we have them, and we're going to get b equals 14 and a equals -15. Right. Next, this is extremely easy. I don't know why this is even here. It's just you just differentiate and substitute points in. So you're just going to differentiate. There's no fractions, so it's really easy. It's just simple power rule, nothing special. Then we're going to derive again to get a second order derivative, and this is the next part. Everything that has a stationary point x equals 1 is just showing that f dash of 1 equals 0 because we know the gradient is 0 at x equals 1. Of course, you would have to show this by actually like computing it on, or not computing, but showing how you get 0 by writing it down on your exam paper. But here you know what I'm talking about. And same with the next part. So you know that when you substitute 1 into the double derivative, it will be 0, which means that it's a point to inflection, but also you need to prove that the points next to it are increasing and decreasing respectively, so we know that it is there is a point of inflection. So you substitute like 1.1 and 0.9, and we can see that one of them is above 0 going increasing and one of them is decreasing, which means that it is a point of inflection. Right, we've got the last question here. This isn't really as much stationary points as it is area and volume. But they snuck radians in here, which isn't that bad as long as you know the formulas, which are pretty simple. So even if you don't know them, you should if you get told them, then you should probably know how to use them. So firstly, we're going to find the volume here. We just need to find the area of one of the sectors, which is half r squared theta times the height, which you could simplify down when you substitute the 0.8 in, because that's what theta is, and we know that it equals 240 from this info that we have here. Next, we're going to simplify this to get h equals 600 over r squared, and then we're going to find the surface area, or an equation for the surface area. So just finding the top and the bottom, and then finding the arc length here times by the height, and then just these two rectangles here as well. Next, we're going to substitute theta into the surface area, and this is going to be our equation that we substitute 600 over r squared into, just to get our final answer for part A here. There should not be a negative there, I don't know why it's there, but it is just 0.8 r squared. Right, next part, we're going to differentiate it to get this, and we're just going to solve for r to get that. That is literally all we have to do. I don't know why it's 4 marks, to be honest, but compared to the last point, but we're not going to be complaining about 3 marks. Next part, we're going to double differentiate to get this, and we're just going to substitute 10.2 in, and we get that it's 5, which is greater than 0, which means it is a minimum, because that is the double derivative. That's how it works. Right, thanks for watching, guys. Bit of a shorter video today again, but I'll come back with probably another AS paper next week, and I will see you that time.